The box of pennies demonstration shows how systems tend to proceed from order to disorder as time goes on. At the top, the pennies are all heads up and separated from some empty space. That's a state we call low entropy. As the box gets shaken, though, it's unlikely for the pennies to remain in that state. We have an intuitive sense that they will eventually spread out and not be all heads up over time. They're proceeding toward a state we call high entropy. And so what is the reason why they do that? Why does it proceed from one to the other? And the answer comes from the mathematics of probability. And so if you look at what is called a tree diagram for flipping a coin, you start on the left and you draw two branches for what could happen when you flip the coin. It could land on heads or it could land on tails. It's a 50-50 shot, 50% chance that it would land on one or the other. That's the first toss, though. If you want to toss another coin, then you got to draw branches off of that, but do it on both. Because whether you go to heads or tails, you're going to flip the coin again, you know? That could land on heads or tails. That's the second toss. In this tree here, we've got the first toss shown and the second toss and the third toss. Now, in my box, there are 8 pennies getting tossed here. But I didn't want to draw the tree for all 8 flips because it would actually be enormous. So I'm just going to use this example of just 3 pennies to show why it's unlikely for the pennies to stay in the configuration that they were originally in. So in order to examine what it's like to just get 3 heads in a row, in these tree diagrams, you imagine just drawing the path of a person who flips the coin and it lands on heads 3 times in a row, right? Then you write the outcomes at the end of the tree. Okay, so the outcomes would be H, H, H for that path. But it would be HHT if you were to take this path. And then HTH. And I'm just drawing these different configurations of what could happen. All in all, there are 8 possibilities for 3 flips of a coin. And what this is supposed to show is that there are many more ways for things to be disordered than there are for them to be ordered. See, here we have all 3 heads in a row. But that is only one case out of 8. So the probability of getting 3 heads in a row on 3 coin tosses is actually just 1 in 8, which is about a 12 or 13% chance. If you flip 8 coins and do this same analysis, you'll find that the probability, this is heads on 3 flips. So what's the chance of getting heads? Well, all heads on 8 flips. I'll tell you. It is 1 in 256. Approximately 0.4% chance that that could even happen. And that doesn't even take into account the positions that they're in. So it is very unlikely for the pennies to stay in that state that we had originally put them in. And this is actually just an analogy here for physics. There's a phenomenon which is so fundamental to physics that it's been given the name, the second law of thermodynamics. The first law is just that energy is conserved. We'll look at that later. But the second law is the one that we'll look at here. Imagine a hot cup of coffee. In some cooler room temperature settings. When we draw the particles of the air around the cup, on average, the particles aren't moving too fast because it's cold and the temperature is related to the speed of the particles. But the particles in that hot cup, on average, they're moving quite fast. Now, it can be shown that over time, the energy that the hot cup has will spread out to the surroundings. There will be a heat flow, Q, which leaves the hot and goes to the room. And so the pennies in the box is actually just an analogy for this same situation. You see, the pennies represent the hot coffee. They represent the energy in the coffee. And the empty space represents the cool surroundings. And just as the pennies tend to flow from the left side of the box to the right, the energy will flow from hot to cold. That's the second law of thermodynamics.